So water exists in a state of dynamic equilibrium. And what this means is that water is always constantly changing back and forth between two forms. And these two forms are down here. So we can see we have two water molecules here, and occasionally this hydrogen will pop off and jump over to this molecule here to create what's called a hydronium, which is H3O+, and a hydroxide, which is OH-. This is dynamic equilibrium, which means that it's going this way and this way at about the same rate. So it's constantly making hydronium and hydroxide, and then they're constantly reforming back into water. One way that we like to use to simplify this is to say that H2O is constantly breaking down into H+ and OH-. So this would be a hydrogen ion, and then this is hydroxide. This is a simplistic way of illustrating this reaction. So the reaction that's actually happening is making hydronium and hydroxide. But for simplicity of talking about acids and bases, we can look at just the concentration of hydrogen and hydroxide. So if we have a solution that's only water, so imagine it's just H2O and it doesn't matter how many H2O molecules it is, as long as there's nothing else in there but water, we're always going to have the same amount of hydrogen ions as hydroxide ions, because one water molecule breaks into one of these and one of these. And this is what makes pure water neutral. Something that is neutral is going to have exactly the same hydrogen as hydroxide. When we add other substances to solutions, they can change the concentration of hydrogen ions, and thus they can change the chemistry of that solution. So an acid is a substance that increases the concentration of hydrogen ions. They're going to do this by breaking down in water and donating some hydrogen ions. So for example, we have HCl is a strong acid. When you add HCl to H2O, that HCl is going to break down into hydrogen and chlorine. And because it adds hydrogens, it's going to increase the concentration of hydrogen ions, which is what makes it an acid. When this happens, the pH will go down. A base is a substance that reduces the number of hydrogen ions in a solution. So this is going to bring the number of hydrogen ions down. So a strong base, so something like potassium hydroxide, when it gets in water, it's going to go into potassium and OH-. And what's going to happen is that OH- is going to bond with some hydrogen ions to form water. And now that hydrogen ion has been pulled out of the solution, and that's going to cause the pH to go up. The only thing that distinguishes a strong acid and base from a weak acid and base is how much they disassociate. So both hydrochloric acid and potassium hydroxide are both strong because they completely dissociate. A weak acid, such as carbonic acid, like this, when it gets added to water, it dissociates into H+ plus HCO3-. So you can see that one of the hydrogens got pulled off, but the other one's still attached, and so that makes this a weaker acid. It can still shift the pH balance by adding a hydrogen, but it isn't going to shift it as strongly because it's not going to completely disassociate. So here is the pH scale. The pH scale is a logarithmic scale that runs from 0 to 14. An acid is anything that has a pH of less than 7. So you can see our picture here of an acidic solution. And you can see that an acidic solution has a high concentration of hydrogen ions, but it has a low pH. So do not get those two things confused. A high concentration of hydrogen ions indicates a low pH, so anything from 7 to lower is going to be considered acidic, where it's going to have more hydrogen ions than it does hydroxide ions. Neutral is anything where the concentration of hydrogen ions is equal to the concentration of hydroxide. And you saw this in our example with water. So this one has exactly 5 hydrogens and exactly 5 hydroxides. This solution is just water. There's nothing else in it. Pure water is exactly 7, Everything else is slightly off. Human blood and tears are at 7.35 to 7.45, so slightly basic. And then a basic solution is going to have a pH of greater than 7. And this is because it has a low concentration of hydrogen ions, which is going to result in a high pH. So anything from just over 7 all the way up to 14, you can see that it has very few hydrogen ions. And thus it has less hydrogen than it does hydroxide, and it's going to result in a very basic solution. So most of our biological fluids, you can see urine can actually change anywhere from fairly acidic to fairly basic, depending on what you are excreting. Saliva is slightly acidic. Human blood and tears are slightly basic. Your small intestine is slightly basic because your pancreas secretes high pH solutions to combat the secretions from the stomach, which are extremely acidic. If you've ever had stomach acid or acid reflux or heartburn, one of the things that's recommended is to take milk of magnesia, because milk of magnesia is a basic drink, and so as you drink it, it helps to neutralize the acid in your stomach. And if you've ever been stuck on the side of the road with a car battery that doesn't work and it's completely corroded, you can actually pour soda on a corrosion on a car battery, because the soda that you drink is extremely acidic. So black coffee, beer, soda, some of those drinks are extremely acidic. And this is actually one of the reasons why eating citric fruits can be bad for your teeth. If you eat so many and then go brush your teeth right away, the acid can actually wear away at your enamel. One other thing to remember is that this pH scale is a logarithmic scale. So every time you see a jump from one number, that is an increase of times 10 the concentration of hydrogen ions. So when we go from 10 to 9, the hydrogen ion increases by times 10. When we go from 10 to 8, that's 2 steps. So the increase in hydrogen ion concentration is times 100. 10 to 7, that's 3 steps, that's times 1,000. So every step on this ladder basically is 10 times increase. And if you go up 2 steps, it's 100. 3 steps, it's 1,000. 4 steps, it's 10,000. So changing from a pH of 7.3 to 7.5 doesn't maybe seem like a lot, but because the scale is logarithmic, that's too much for our body to handle going outside of that small, narrow range of pH. So for the most part, our cells live very close to 7. We have a very narrow range of pH that our body actually tolerates. So we have several buffers throughout our body that help to minimize the changes. So a buffer is a substance that can either provide hydrogen ions if there's not enough, or it can provide hydroxide ions if there's too many hydrogens. And so a buffer is kind of ability to go both ways. So the buffer can either make something slightly more acidic, or it can make something slightly more basic, depending on whether the solution is too acidic or too basic. So this is an illustration of how human increase in atmospheric CO2 has caused ocean acidification. So what we've done is we've been burning fossil fuels, which increases the amount of CO2 in the atmosphere. And this has been widely agreed upon by climate scientists that this is causing our planet to go through increased warming and all sorts of other effects from the increase of atmospheric CO2. So CO2 actually dissolves pretty well in liquid. So what happens is the huge majority of the surface of the Earth is ocean. So a large amount of CO2 from this airplane will get dissolved into the ocean. And what will happen is it will combine with the water to form carbonic acid. So this is carbonic acid. That carbonic acid is a weak acid, right? So this weak acid will dissociate into hydrogen and carbonate. Well, that hydrogen will actually combine with more carbon from the water to form more carbonate. And what this does is it pulls the CO3 2- away from the places that need it. So corals use calcium and carbonate to form calcium carbonate. And they need the CO3 2- plus the calcium to make their body structures. So the actual physical bodies of corals are made up of calcium carbonate. And then all of the fish that rely on coral structures rely on corals to build their bodies. So if this CO3 2- is getting combined with hydrogen to form this, it's not actually available to the corals to be able to build their bodies. So what ends up happening is the corals are negatively affected because there's a large concentration of CO2 in the water. And so this is what we call ocean acidification. And the pH of the ocean has actually gone down, making it much more acidic. So here's just an image of a coral reef from December 2014, where it was healthy, and you can see all the corals are alive here. Coral is a symbiotic organism where the actual structure is made out of calcium carbonate, and then they have algae or bacteria that live inside of them that give them their pretty colors. By February 2015, so that's December, January, February, that's like 3 months later, they have expelled all of their symbiotic organisms, and this leads to something called bleaching. And without the symbiotic organisms, the corals can't get enough nutrients because they were getting nutrients from the algae and the bacteria that live in them. And so eventually, so this is August 2015, that's later that year, this coral reef was actually dead in less than a year because of acidification of the ocean.